Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. So what's new in the world of science for you then?
It's an interesting story. This one about quite a major greenhouse gas problem. You always think of smokestacks and big chimneys and cars and things, a major greenhouse problem. What you don't normally think of is rural fields full of cows.
Right.
Because cows have guts, which are great big fermentation systems to convert the cellulose in grass into food for them, into sugar, which they can absorb. And the problem is great big fermentation systems get colonised with a kind of bacteria, ancient bacteria, which convert some of the food into methane.
Right. And
the methane escapes.
Yes.
And one of the problems with methane is it's a really powerful greenhouse gas. It's about 20 times as powerful as carbon dioxide.
Mm-hmm.
And so the global cow and sheep, or the ruminant population, is producing about 10% of the global warming effect as all the carbon dioxide we're pumping out. So it's really quite a major effect. But a guy called Alexander Hristov in the States has been experimenting with cows trying to reduce these methane emissions.
Mm-hmm.
He's tried all sorts of different things, but the one he's come up with, which seems to work quite well, is oregano. And he was finding that if you fed oregano to the cows, it could reduce the amount of methane they produce by 3/4. And it's not just that, it's also an advantage because all of the food which gets converted into methane in the cow's stomach isn't getting converted into food.
Right.
So the cows were actually producing, they were saying 3 pounds more milk a day from each of the cows because they weren't wasting all this energy turning it into methane. Could be good news for the oregano growers out there.
It could be, couldn't it? Let's start off with the questions then. And coming up first, this is on the text, and it comes from Richard in Flitwick. He says, how do they make very small things such as a megapixel in a digital camera, and how does it work? Dave?
OK, things like digital cameras are actually made by a very similar process to how you make computer chips. It all basically works essentially with photography. Basically what you're doing is you have an image of the thing called a mask which you want to make a copy of in the silicon, in the actual device you're dealing with. You cover the device which you're dealing with something called photoresist. This is a plastic which when you shine light on it, it changes its properties. It either becomes soluble or it stops being soluble. There's different types. So you basically shine light through the mask onto your silicon chip. And then in some places the photoresist it becomes solid, in other places it's still soluble. You then wash it, so you've got some areas covered in photoresist, others areas which aren't. You then put it in something which dissolves away some of the silicon, and then you get a pattern on lots of different things to the surface of the chip, and you repeat its process lots and lots of different times, and you can build very, very small structures, essentially because you can project the image on it sort of in the opposite way of a photographic enlarger. So imagine a photographic enlarger making a small piece of film big. You can just run the optics the other way around. So you can make a big image much smaller on the chip. So you can make the image very, very tiny. And once you've got all the chemistry and material science right, you can make very, very, very tiny structures down to about 13 nanometers. So that's 30 billionths of a meter across.
Gosh.
Making modern computer chips.
Wow.
And how the sensors on your digital camera work, you've got lots of little regions. With a colour sensor, you've got a little bit of coloured plastic or something over the top of it. Over some of the sensors, so some only let green light through, some only let red light through, and so on. When the light shines on them, that lets electric charge move up towards the surface, and then it basically reads off how much electric charge has moved up to the surface. So you've got some idea of how much light has fallen onto this little tiny square, and then the computer puts together all the information from the amount of light which has fallen onto each of the tiny squares, little tiny pixels, and stores that away as a file which you can then upload onto your computer.
Wow, how about that then? Now, let's go to Dave here. It says, Sue, question, why do we use carbon dioxide in fizzy drink? This must account for a huge amount of carbon dioxide that an alternative could be used.
Well, for a start, the carbon dioxide which they're using is recycled. It's a byproduct of something else because they're not making it deliberately to make fizzy drinks out of. So it's a byproduct of brewing, because brewing beer produces lots of carbon dioxide or some other process. I think, for a start, carbon dioxide is very soluble in water, which means that you can dissolve a lot of it in water, and there aren't that many other gases which are very soluble and not very dangerous. And also, I think, actually, some of the taste, that fizzy taste, the sharp taste, isn't actually just the fact that it's bubbly. It's to do with the carbon dioxide dissolving in the water and that actually affecting your mouth directly and actually stimulating nerve endings in your mouth. It also makes the water a little bit acidic, which affects the taste as well. So I don't think any other gases would work as well, and it's not actually producing carbon dioxide from anywhere else. It's just redirecting it on its way to the atmosphere.
All right, well, let's go for another one here. Well, there's one here that's come in by email this time, and this is from Adrian, actually. And he says, hi, one of the questions I sometimes ask myself while watching the sunrise having a coffee, if the Earth would suddenly stop, how high would I jump? Just the sort of thing you ponder about, doesn't it, when you look at, if the Earth stops, how high would I jump? Dave, what's your take on it?
So there's two different things. Yes, one of this is what happens if it stops spinning, and the other one is what would happen if it stopped orbiting.
Right.
If it stops spinning, let's take the extreme example, you're on the equator. On the equator, you're moving about 460 metres per second, so that's about 1,046 miles an hour. Now, if you ended up moving at that speed straight upwards, you'd stay in the air for about 100 seconds, and you'd go up to about 10 kilometres if there was no atmosphere there. And so you're pretty high up, then you come down and hit the ground. So that would be pretty impressive. However, if the Earth was spinning and it suddenly stopped spinning, you wouldn't be going straight upwards, you'd be going straight horizontally. So essentially you would all of a sudden be going at about 1,000 miles an hour, supersonically. I guess all the air would probably be going at the same speed as well, horizontally. So if you're on the top of a mountain, depends how high you were, you'd start with how far you'd fly. But if you're on flat ground, you just slide across the ground incredibly fast. However, if the Earth stopped moving around the Sun, things would be entirely different. The Earth is orbiting around the Sun at about 30 kilometres every second. So really, really quite fast. And the escape velocity, so the speed which you would have to be shot out of a gun from the surface of the Earth, so as you would leave the Earth and carry on going forever into space, is only 11 kilometres a second. So if the Earth suddenly stopped in its orbit, you would fly off straight into space, and we wouldn't see you ever again. You'd probably go into orbit around. You go straight into orbit around the Sun.
Dave. And you as well, Dave. We'd all just fly off into space.
The people on the back of the Earth would get entirely flattened, and the people on the front of the Earth would get thrown off into space.
Wow! Somebody make a film about that one. Yeah. Let's go to Billy now. He's on the text from Ditchingham. He says, great show, Dr. Chris, it's Dr. Dave. How does food you eat become fat on the body, especially on the face?
I mean, the food which you're eating, it gets absorbed, it gets broken down into very, very small lumps, so into individual sugar molecules, individual glucose molecules, little tiny lumps of fatty acids and fats and things. And then if your body hasn't got anything to do with it, immediately some of the sugars can get taken and stored as a thing called glycogen in your liver. Some of it gets stored in your cells, but eventually your body's still got nothing to do with all this food. It doesn't want to waste it, so it takes the special fat tissues, which then convert it, using some of the energy, into stuff called fat, which is a very, very dense energy store. And again, I'm not a medical doctor, so I couldn't tell you exactly where it gets deposited or why it gets deposited in some places as opposed to others.
We'll let you off that one then. Now then, Bill in Wroxham says, puzzling problem, if the moon is responsible for the tides and there's only one sunrise a day, how come there are two tides? Good question.
It's a very good question. Okay, this is because it's slightly more complicated than what you're thinking. If you imagine the moon is attracting the Earth, and because the moon's gravity gets weaker the further away you go, the water which is closest to the moon is attracted to the moon harder than the Earth is. So the water which is closest to the moon gets pulled away, forming one bulge, so that's one tide a day. But the Earth is reasonably rigid. It does actually get tides in the Earth, but relative to the water it's reasonably rigid. And the Earth is pulled towards the moon more strongly than the water on the far side. Mm-hmm. So the water on the far side gets left. Earth gets pulled away from the water on the far side, so you're left with a bulge on the other side. So there's one bulge closest to the moon because it's getting pulled towards the moon. There's another bulge on the far side because the Earth is getting pulled away from the water.
Right.
So the water gets left away, so you get two bulges. The Earth spins underneath those two bulges, and so as you go round, you see two highs and two lows. So you see two tides a day.
Let's go to our next question. Oh yes, here's a good one. Now Chris says, why do pigeons nod their heads when they walk and other birds don't? Dave?
That's a really good question. It's a question which I was actually interested in, so I thought I did some actual research of my own for this one. I got my high-speed camera out and pointed at some pigeons who were walking around outside in the garden. So I've got some slow-motion footage. It's actually on our website in nakedscientist.com in Kitchen Science and Garage Science. If you look at the video, Garage Science, things which you might not be able to do at home. If you watch the video, what's actually happening when the pigeon bobs its head is it moves its head as far forward as it can go, and then it keeps its head absolutely still compared to the rest of the world, and then its body kind of catches up and the head moves back as far as it can go, and then it suddenly moves it forward really quickly. I think the reason why it's doing this is because it's trying to keep the world as still as possible. Because if the world is still, it's much easier to notice things moving against the background. So if there's a cat creeping up on it very slowly, it's much easier to see that if the rest of the world is absolutely still in its visual field.
Yeah.
It takes much less processing power, much less brain to be able to decode the fact that the cat is moving, because it just means that if there's something moving across its eye, then something is actually moving, so it might be coming to try and eat it. And so it's a cunning strategy to save a whole lot of basic computer processing in its brain, so it can get away with a smaller brain. Some of the birds do it.
Chickens do it,
Chickens
don't they?
do it.
Yeah.
Quite a lot of other small birds do as well.
Yeah, because chickens, if you notice a chicken, and I've got to do this, they kind of scratch with the feet, and then they look, they stop motionless, and then they just get something quick, which is, that's why they do it.
It's doing the same thing. Right. And also, I think if you pick up a chicken and then move its body around a little bit, its head stays completely still.
Yes, I've done that. I had that before, yeah. Yeah, because you think, what are they thinking? And do chickens think? Probably. Let's go to another one now on the text. No, on the email, sorry. Ian in Wyndham, thank you for emailing in. Why does electricity always want to earth itself? Where does it go exactly? Surely it has to get back to where its source somehow to complete the circuit. Dave?
Yes and no. Mostly, basically anything electrical which is plugged into the mains, pretty much anything. At some point, one side of the mains is connected to Earth. It's a safety feature. It basically means that if you've got a metal device in your house and one of the wires falls off inside, then that wire touches the outside case, and then electricity, instead of flowing through you next time you grab hold of it, will flow back through the Earth cable to Earth. Get a large current flowing, and that blows the fuse, and so everything's now safe. And so basically almost all the mains are attached to Earth, and so one end of the one of the two wires is attached to Earth at the substation, and so electricity can complete the circuit by flowing through you to Earth and back to the substation. You do get some things which aren't Earth, things like the transformers for shaver sockets in bathrooms.
Yeah. Neither
of the two ends of that are earthed. So if you end up touching one of the two contacts to Earth, the circuit isn't complete, and so you're relatively safe. The only way you can get current flowing through you is if you attach to both of the contacts inside the shaver socket.
Right.
But if you have a battery or something where neither end is attached to Earth, then, like the isolation transformer, then it doesn't complete the circuit. It's just because the Earth conducts electricity reasonably well and it is completing the circuit.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Here's a good one. Jeff in Grey says, what does Dave think about the Americans using imperial measurement when their future, Star Trek, uses metric? Why do they persevere? How brilliant is that, Dave?
That is brilliant. It's, I think, just inertia. I mean, why do we still use miles an hour? Because it's hassle and effort and money to change. Mostly effort on our part to learn a new unit system. I can measure distances which I'm going to walk in kilometres, but when should I drive in miles? Just Americans haven't got quite so far through the process of metricating as we have.
Right, let's go to one here. This is from Bill Unsworth, who says solar sails. How is momentum conserved when using solar sails? Interesting one. Dave?
Indeed, yeah, solar sails are getting quite fashionable these days. The Japanese launched a solar sail which is going to Venus, basically,
really?
And the Americans have been launched a test one recently. The idea is that you've got a great big mirror,
Mm.
And then light shines on. If the light shines on the mirror, it bounces off. And light, although it has no mass, it does actually have a little tiny bit of momentum. And so when the light bounces off this mirror, it pushes very, very gently on the solar sail. And so the sail gets a force and it accelerates. So how is momentum conserved? Essentially because if you're standing still, it looks like the light reflecting off the mirror. It's got ever so slightly less energy, very slightly longer wavelength, very slightly less momentum than the light which hits it. And of course, actually the main thing is that light has momentum, so when it changes direction, its momentum changes direction, so the solar sail gets a slight push.
So they're only using them on spacecraft? Are they using them anywhere else?
Because the force is absolutely minute. You're talking sort of postage stamps on areas of hundreds of square metres. The real advantage, though, is it doesn't require any fuel.
Right.
So although the forces are very, very small, they can carry on pushing and pushing and pushing as long as you've got sunlight.
All right, there's one here on the text here that's come from Sue, who says, Dr. Dave, are cows the only animals producing methane? It seems there should be others, and that would increase that 10% figure. From Sue.
The 10% figure was for all of the ruminants, so cows and sheep and goats. So that they produce the most methane, and other non-ruminant animals will produce some methane, but much, much less.
John in Bletchley has a question about bees. He's called in. He says, about bees, do they go back to their hive at night? He has lilacs in his garden and bees aren't around at the night.
I think so, yes. Bees, at night it gets cold, it's dark, so they can't see. They'd have difficulty keeping themselves warm enough to be able to fly. You've got to be a certain temperature for all the chemical reactions in their muscles to work fast enough for them to be able to fly. So yeah, I think bees do go to sleep at night. Certainly the bees in my parents' garden do.
All right, well, they go and tuck themselves up in their little beehives. Let's go to Ian, who has asked a question here, Dr. Dave. He says, if I had a power source and a light bulb attached to the same wire and plugged both ends of the said wire into the ground, would the current be completed through earth and the bulb illuminate? Dave.
It does slightly depend on the earth. If you have a large enough piece of good enough earth, so if you have a large enough piece of copper put into the ground at both ends of your wire, then the resistance will be relatively low. I think you can get down to less than an ohm, and you could certainly complete a circuit through a light bulb and it would light up. Especially if you lose some of the voltage in the earth, especially if you didn't have a particularly big copper stake in the ground.
Sure.
But certainly you could do.
All right. Another one here that's come through on the text and says, Dear Dr. Dave, what is a ramjet and could it ever work for human space travel? Ooh, what is a ramjet? Dave.
Okay, a ramjet, basically the way a normal jet engine works,
Yep.
The idea is you take air in the front end, you compress it to squash it down a bit, you then mix fuel with it, ignite it, it gets very hot, it expands, and it's easier for the air to get out of the back than the front, so the air keeps on going out the back, because the air is pushed out the back. Every action has an equal opposite reaction, so you're pushing the air out the back, so the air pushes the plane forwards. The way a normal jet engine compresses the air and squeezes it into the front of the engine is by using a whole series of turbines, which are turned by a sort of basically a windmill arrangement at the back, another turbine at the back. And so air gets taken in, blown out the back, and all's well. The problem is if the air coming in gets faster than the speed of sound, you get all sorts of horrible shock waves which interfere with your turbines, and all sorts of bad things happen. And so you can't, the air inside, the air going into the jet engine's always got to be slower than the speed of sound. So things like Concorde has got special baffles to slow down the air going into the jet engine.
Oh, wow.
And once you start going fast enough, that becomes a really big problem. And you then got to accelerate at the end, it all becomes very inefficient. So the idea of a ramjet is to do this compression just by the air coming in faster than the speed of sound, very, very fast. Just because it goes through a kind of constriction, then it gets compressed by going through the constriction, it gets to the other side. You throw in some fuel, you burn it, and stuff comes out the back. The problem is it's got to be going very, very, very fast to start working. You also get things called scramjets, where everything is happening faster than the speed of sound. So you get supersonic combustion. So the actual combustion is happening faster than the speed of sound, which is very, very difficult to deal with, because as soon as things go faster than the speed of sound, everything gets much more complicated. And people are suggesting that this would be a way of reducing the size the rocket needs to be to fly into space, because most of the fuel in a rocket is used to lift the fuel in the rocket. Because if you want to get a little space capsule into space, you've got to have the fuel in the rocket to lift it the last 10 miles. And then the 10 miles below that, you need the fuel to lift the fuel and the capsule. And below that, you need to lift the fuel and the capsule. So the rockets get bigger and bigger and bigger as you go further. And so it becomes very inefficient. And most of the weight of the fuel is in oxygen, because space rockets, they take their oxygen with them. And 70-80% of the weight is in the oxygen. So if you can get the oxygen from the air while you're still in the atmosphere, that could save the amount of fuel you need to lift, which saves fuel you need to lift, which saves fuel you need to lift. So you could, in theory, make space rockets much smaller. Problem is, building ramjets, especially supersonic ramjets, is very, very difficult. They're only just about getting the hang of it.
Oh, it's much nicer to stay local, I think. Let's see what else we've got here. We've got a few more minutes left. This one is from the email from Ed. Dear Naked. Dear Naked, you're talking to Dr. Dave here. Why does water freeze outside the freezer?
Is he talking about sometimes if you get a bottle of water really, really cold in a freezer, and it's still liquid in the freezer, and you take it out and you pour it out and it freezes in front of your eyes?
Yeah.
This is an effect called supercooling, because we can actually cool water below 0 degrees centigrade and it stays a liquid if the bottle is very, very clean, because starting to form an ice crystal is actually very difficult. And so it takes quite a lot of energy. So unless there's already an ice crystal in there, you can actually cool water, I think actually really quite low temperature, like minus 10 degrees centigrade, if not lower, and without it actually freezing, as long as everything's very cool, very still. As soon as you pour it out, the water hits the glass, hits some dirt on the glass. Around dirt, it's much easier for ice crystals to form. Once you've got an ice crystal there, that can grow and grow and grow, and the whole thing can solidify.
Wow.
It's very like those hand warmers. Have you ever seen the clicky hand warmers?
Oh, yeah, they're great.
Ones which are kind of, which you boil to reset.
Yeah.
And you click a thing, and then they kind of all solidify and get very, very hot.
Yeah.
Exactly the same idea. Then you've got a super cooled, it's actually sodium acetate solution. Basically salt and vinegar flavouring crisps in very large quantities in a bag. And as long as the bag is very, very clean, no crystals can form, and it's really quite stable. Inside that clicky thing, you get a few crystals which are trapped in the clicky bit. When you click it, some of those are released. That triggers crystal formation, and the crystals grow and grow and grow. And as the stuff crystallises, it releases lots of energy, so it gets hot.
John in New York State says you can run a watch off an orange. Have you ever done that?
I have. I've actually charged an iPod with it, or a phone with it, with lots of oranges.
Have you?
36 of them.
How science is mad. All right, one last one here, which is from Darren. Why do IR cameras use red-looking light, but the images appear green? How does that happen?
Okay, the infrared camera is sensitive to all sorts of... is sensitive to light you can't see. So the actual light which it is seeing is actually invisible. So the colour which your eyes see is entirely a figment of the technology which you're using, so the mechanisms inside the camera. In fact, with modern ones, the colours which come out are entirely random, because essentially modern infrared cameras are basically a camera which you plug into a TV screen through a computer, and the colour which comes out just entirely depends on how you designed your TV screen. One of the reasons why they tend to use green is that your eyes are most sensitive in the green region. So especially the older fashioned versions, basically they worked by light would hit the front of the detector, that would knock some electrons off the detector, they would get accelerated down a tube. As they move down the tube, they'd bash into gas molecules and knock more electrons off those gas molecules, and so you get lots of electrons. They then hit a screen at the back, which produced green light. And the reason why they picked a substance which turned the electrons into green light is because your eyes are most sensitive. So that means you can see the most dim things because your eyes are most sensitive to the green.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, Look us up online at nakedscientists.com.